I first like to make a confession. This talk is slightly off. It will not emphasize so much on the dynamos, but on the instabilities, and we'll also look at sort of astrophysical systems which are very different. So these are plasmas that I'm talking about, not liquid metals. And I'd be happy if you interrupt me in the middle if something is not making sense. Okay, so to set the stage, okay. So to set the stage of what I'm talking about, basically I'll be talking about buoyancy instabilities in weakly collisional magnetized plasmas which occur in galaxy clusters. And galaxy clusters are probably the largest gravitationally bound structures in the universe. And this is a snapshot from the Millennium simulation which shows the clustering and formation of structure in the universe. And these are filaments made up of primarily made up of dark matter, and because gravity is gravitating systems are inherently unstable and they'd like to form clusters and filaments, this is what our universe looks like at the largest scales. And at the intersection of these filaments you get these clusters, so which are virialized structures. So they are roughly, these are spherical systems, these are virialized, that is the kinetic energy of particles and the gravitational energies are comparable, whereas these filaments are not virialized. That's why these are spherical. So I'll be talking about these galaxy clusters. This is dark matter snapshot, but what I'll be talking about is normal matter, which is sort of confined gravitationally by the gravitational pull of this dark matter. So this is an X-ray image of a galaxy cluster, and it shows diffuse X-ray emission, okay? And this is the same galaxy cluster looked in optical, and it shows red and dead galaxies. And overabundance of galaxies in particular region is sort of how you identify a galaxy cluster. So what I'll be concentrating on is the dynamics and thermodynamics of this hot plasma, which is confined by dark matter. So we won't really be talking about dark matter after this. This is just to set the stage. So I'm also going to be talking about the equations that you guys are all fond of, but I just wanted to give a background. Okay, and dark matter just provides background gravity. Okay, and just to sort of calibrate our scales, this is sort of temperature density distribution of different types of matter that we are familiar with. This is Earth's core, this is solar core, high density for me, and relatively lower temperature. What I'm going to talk about is the intracluster medium, this diffuse X-ray emitting plasma, which is about 20 orders of magnitude lower density compared to these systems. And because of that, the properties of this medium or this plasma is very different. Okay, so it's about 1 to 10 keV. It emits X-rays after all, and it's about 10 to the minus 25 10 to the minus 25 grams per centimeter cube. This is SI. We astrophysicists use CGS. Okay, so just to give you some typical numbers for this medium, the mean free path of this plasma is just 1 over n sigma, where sigma is the collisional cross section, is about 0.3 kiloparsecs. Actually, again to set the stage, the scale that we are interested in here, this is the core of cluster, is tens of kiloparsecs. Okay, so tens of kiloparsecs, and this is the mean free path, point few kiloparsecs. So the mean free path is only 2 or 3 orders of magnitude smaller than the scales of interest. Okay, so this medium is very viscous. Okay, in a traditional sense. The other important point here is that this plasma is magnetized. Observations of Faraday rotation has shown that these clusters have magnetic fields of order microgauss, which is similar to Earth's, similar to the galactic disk magnetic field strength. Right. So if you put in this magnetic field, and you can calculate the Larmor radius of an ion, and it's tiny compared to the mean free path. So basically the picture is you have these particles gyrating over very, very, very small orbits and going very, very long before colliding with another particle. Okay. So if you use the parallel mean free path, the Reynolds number is about 100, which is very viscous. But if you use the perpendicular diffusion length, the Reynolds number is extremely huge. So this medium is extremely anisotropic because it's magnetized, and all transport properties like conductivity, viscosity, particle transport is expected to be very anisotropic. One thing, one sort of note of caution is you cannot take these numbers literally, because plasma is known to be extremely unstable. So you cannot just plug in and say that, oh, the anisotropy of transport will be that enormous. Some small scale instabilities will almost always do something to break this down. This anisotropy of transport in plasmas is very nicely illustrated by these loops observed in the sun. What you see here is an X-ray image of the corona, and you see these loops, and the reason you see your eyes can make out that there are these nice structures is because there is very large gradient in the emissivity across these structures, but none along these structures. That means particle transport is very efficient and makes the density almost constant along these things. That's why you intuitively feel that these are magnetic fields. Okay. So this is a sort of visual example of an isotropic transport. So this is a pictorial representation. So if you have an isotropic gas, this is how a particle would diffuse in such a medium. You'll have random motion, there's no preferred direction, and stuff diffuses equally in all directions. And you can use a conductivity, a heat flux which is minus kappa grad T, where kappa is the conductivity and T is the temperature. This is good for a gas or an unmagnetized plasma. But on the other hand, if you have a plasma, as I already told you that particles are mainly sort of moving along field lines. So you just have, for example, heat transport along magnetic field lines, which is represented here. So this heat flux is along the local magnetic field direction, and it's proportional to the temperature gradient calculated along the local field line. Okay, and this I already mentioned that the parallel diffusion coefficient is much larger than the perpendicular diffusion coefficient, and it's just because the step size, the mean free path is replaced by the Larmor radius, which is tiny. Okay, so let's come to the equations. So these are our usual, so just to set the stage, what I'm going to do is going to do a calculation for what is the natural convection or buoyancy response of such a system. We know that if you have an adiabatic fluid, that the adiabatic fluid becomes convective when the entropy is maximum at the bottom. So this is an analogous calculation for an anisotropically conducting plasma. Okay, so we have mass conservation. This is the momentum equation. This is the ideal induction equation, and then this is the energy equation. Normally for an adiabatic fluid we set the entropy is constant, but since we have conductivity, entropy of a fluid element is not constant, it sort of diffuses. Okay, so these cluster plasmas are high beta plasmas. They are magnetically subdominant. So the Lorentz force is small compared to gas pressure force, for example. So basically to zeroth order, the background balance is between gravity. dP dr is minus rho g. So this is sort of the linear analysis. This simple textbook stuff actually, but no one did it because no one was interested in these anisotropic stably stratified plasmas. So gravity points in minus z hat direction, you have magnetic field which is weak, but it is important for transport. Although magnetic field is dynamically weak, it modifies the transport of particles enormously. So this is the background hydrostatic equilibrium. Now we do local WKB analysis, we have an equilibrium, we expand the perturbed quantities in this local plane wave form, and so we assume B to be in the xz plane and K to have any general wave number. And if we plug in this form of perturbations in these equations and assume the Boussinesq approximation, that is we filter out sound waves, what we have are these buoyancy waves, okay. And without really going through the tedious calculation, actually I am writing down the dispersion relation here, okay. So this omega is the wave frequency, and omega conduction is some conductive frequency which you define based on the conductivity. It's like K parallel square diffusivity, thermal diffusivity. So let's go to the regime, say omega conductivity is 0, that is if you are in the adiabatic regime, what you have is just these two terms, and you have omega square equals n square K perp square by K square, which is normal natural convection, okay. And if your stably stratified n square is positive, Brunt-Weissela oscillations. If on the other hand you are in the regime where conductivity is very large, which is the regime for these galaxy clusters, you balance this term and that term, and you get a modified sort of a modification of buoyancy oscillations in presence of conducting plasmas. And you can see that this n square, the Brunt-Weissela oscillations, are governed by background entropy gradients, whereas this is governed by background temperature gradients. And it is sort of natural to expect, because if you have large conductivity, the magnetic field lines want to be isothermal. So that's why a temperature gradient plays an important role rather than the entropy gradient. So I'll sort of describe this pictorially in a bit, but just wanted to set the stage with the equations. So this is what I was talking about, Schwarzschild convection. So if you have an adiabatic fluid, I'm sorry this is sort of too simple, but anyway I thought there are some people in the audience who look young, so I'll go through this in a little bit of detail. So basically when we do convection, what we assume is that you have a background atmosphere which is in hydrostatic equilibrium, and you take a blob and you displace it by a small displacement, and you look at the blob at the new position and ask whether it's heavier than its background or lighter than its background. If it is heavier, it will come back, so that's stable, and unstable in the other case. So basically what you do, we are after rho star minus rho naught. So rho star minus rho naught star, basically the difference between densities of the background and the blob. So rho naught star is just obtained by Taylor series expansion of the background density given by this. The rho star, the density of the blob, is given by this adiabatic assumption that as you move this blob, it's not losing heat or gaining heat to its neighbors, and you just do this, you get this. So rho star is this, rho naught star is that. When you take the difference, you can sort of get it in this form. So this is the buoyancy force, rho star minus rho naught star g, and this looks like n square, the Brunt-Weissela oscillation frequency square delta r. So you have a harmonic oscillator, which you should always have when you do linear analysis. So you see that the stability is governed by the background entropy gradient. Okay, so now sort of, I motivated the linear dispersion analysis, but we can also look at the same, we can make an analogous picture for these instabilities driven by anisotropic conduction. Okay, so assume that gravity is in this direction and temperature is increasing as you go to the bottom. Okay, so it's hottest here, cooler up there. So this is the dashed line is the unperturbed magnetic field. Now you perturb this magnetic field. Remember, tension is not important. Magnetic field is not dynamically important, so you can ignore tension at least for now. So, but conduction is fast. So this magnetic field line is isothermal. So this blob has the same temperature as this blob, and all of them have the same temperature as this dashed line. Okay, but so now look at this blob. This has the same temperature as this guy, but the background temperature is higher here. Okay, so the background temperature is higher. This temperature is lower. So density is higher, right? Because NT, it's always, in both cases, it's always in pressure equilibrium at a given height. So since this is cooler than the background, this is heavier and it would sink. So basically it's even simpler than the previous case because you didn't have to do any Taylor series expansion because the field lines are isothermal. But if you do the mathematics, you get this. So what this means that if your temperature is maximum at the bottom and if your conductivity is large, this is an unstable configuration. Magnetic field lines would want to become vertical. Okay. And if we look at this, so dt dz negative has an instability, but dt dz positive also has an instability because you can choose your magnetic field direction so that is satisfied. So there is another instability which is slightly more difficult to explain in this simple picture, but that occurs when the temperature increases with height, and that instability has a tendency to make magnetic field lines horizontal. Okay, so let me show you a simulation. What is shown here are magnetic field lines, and actually these are one of the early simulations when my friend Ian was doing these calculations. So you have reflective boundary conditions at the top and the bottom. Okay, and the initial field line is horizontal, and you can see the instability taking off. But since you are not allowed to make the magnetic field lines open in this setup, they sort of get stuck. Okay, but you do see that tendency of horizontal field lines to become vertical. If we allowed the magnetic flux to leave the box, they would become all vertical, and I'll show you that later. So this is sort of a numerical simulation of the first instability, which I described pictorially here. This is called magnetothermal instability because it's the combination of thermodynamics and magnetic fields which causes this. The other instability happens when temperature increases with height. So temperature is minimum here and maximum there, and all this is okay in galaxy clusters because we have an extended matter distribution, like, you know, and the virial temperature has this general shape. It's not, I mean, it's difficult to imagine how can you have temperature increasing with height. Of course we do have it in the stratosphere and so on. It really depends on heating and cooling properties. So we do have both of these regimes where temperature increases and the temperature decreases with height, and therefore these instabilities are important in galaxy clusters. So these are 4 snapshots of the other instability. And this instability has a tendency to make magnetic field lines horizontal. So temperature is lower here and higher here, and this instability makes field lines horizontal. So it sort of shuts off conductive heat, right? If fields were vertical, there's large conductivity along field lines. You could bring in a lot of heat from here to here. But if you make your field lines horizontal, thereby cutting off conductive heat, you can sort of prevent that heat flux coming from top to the bottom. Okay, so this is a compilation of temperature profiles of different clusters, and you do see that there is an inner region where temperature increases and an outer region where temperature decreases. So you have both of these instabilities at least possible. Right. So we have talked about the linear instability, but the question is how do these saturate and what happens in the nonlinear state. Okay. So this is the HPI, which is you start with temperature increasing with height, it will make the field lines horizontal. So, and this is what you see. So this is at 0 time, this is 3 buoyancy time scales, 12, 17 and 50. If you wait many buoyancy time scales, it sort of makes the field lines horizontal. There is no, there is very small fluid motion in this stage. So basically what has happened is this state was linearly unstable. All it does is make it like this, and then there is no drive further, there is no further drive to keep this instability going. And it's easy to see because so this end state is almost like as if you have a horizontal field line, okay, and your temperature is increasing with height. So if you perturb it, if you perturb the saturated state like this and assume that the pressure remains the same at the same height, you'll see that there's a restoring force which tries to bring this back to its original position. So the initially unstable state has been saturated and now it's totally stable. Okay, and that's because to make these field lines vertical again takes work. Okay. So basically the saturated state of this instability is very simple, it just field lines just become horizontal. What about the other instability, the magnetothermal instability, which is driven when the temperature is the maximum at the center? So in this case you start with horizontal field lines. So these are also snapshots from simulations. These white lines indicate that there is a temperature gradient there, but these regions are isothermal. These are just there so that there is no abrupt boundary. So what you see is that these horizontal lines become vertical and but then they end up in turbulence. So this saturated state is not like the previous one. Here you have sustained turbulence in the nonlinear stage, and the reason for this is also quite simple. You start with horizontal field lines, make them vertical, and if you perturb the field lines in the horizontal direction again, there is no buoyancy. You don't need to do any work to move fluid elements in the horizontal direction. So if you have a vertical field line in this state and if you perturb it like this, there is no work needed. And once you have horizontal field lines because of magnetic flux freezing, that's unstable to this instability, so it will sustain. So this is nonlinearly sustained. So what so this has been sort of, so when I did the previous calculation for the heat flux instability, I thought this instability will also be sort of fizzle out, but that's not the case. It's because it requires horizontal field lines, and it's easy to make horizontal field lines because this direction is neutrally buoyant. So basically what I'm saying is in these galaxy clusters in outer regions where this instability is going on, these can lead to magnetic field amplification and some sort of a dynamo. So rotation is not very important. So it will be something like a turbulent dynamo or an alpha square dynamo. So there's been a bunch of work sort of generalizing these ideas to include viscosity. Since conductivity is important, viscosity should also be important, but it's not as important as conductivity, because in a plasma with an electron and ion temperature, with the electron and ion temperature same, the ions are a factor of 40 smaller, they have a smaller speed. That's why viscous diffusion is smaller. So conductivity is more important than viscosity, but viscosity is not negligible. So these is work that emphasize the importance of viscosity in all this work. Then Sagar here and his collaborator have studied the importance of abundance gradients. So these galaxy clusters have metallicity gradients that can give rise to force because of variation of the mean molecular weight. So these are sort of things that have been done. So this is the summary. Actually, so this HBI, the instability that just makes field lines like this, is not that important, because all it does is this, and just sort of, there's no sustained turbulence. Okay, and the other thing is magnetic tension and viscosity can suppress the horizontal instability further, but this MTI, the magnetic, where the magnetic field lines becomes vertical, can be important in generating magnetic fields in galaxy clusters. And there are a whole lot of issues regarding this setup, in the sense of the mean free path is of order the scales of interest. So this is formally a collision-less plasma. How can you treat it like a fluid and so on? These are actually valid points, but I am sort of a, so Alex Shekushkin, who was here previous week, sort of has done work on this, and I have also been involved with this, but I am sort of, since the mean free path is at least 10 or 100 times smaller than the scales of interest, I am happy here. But there are hot accretion flows where mean free path is larger than the scales of interest. There, of course, one has to worry about plasma instabilities. And I think the small scale instabilities which scatter particles will make the plasma behave as if it was collisional. Right, so these transport, the change of transport properties of this intercluster medium should also affect like thermal transport and dynamos of these plasmas, and there are implications for astrophysical problems such as cooling flow problems and estimating cluster masses by assuming hydrostatic equilibrium. Thank you. Right, so one problem or one difference between this and solar atmosphere is beta there is 1. I mean, so magnetic forces, so basically if you go to this picture, for example, this picture, the magnetic tension will sort of stabilize you. So, you know, this is a situation where tension is not that important. Yes, 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 yes. Right. Galaxies and clusters can be like that. Yes, ma'am.
One suggestion for making unstable is MRI.
Yes.
Now, MRI has this magnetic field, should not be too large. So, this is a strong candidate for making accretion possible, or?
No. This is sort of, there's no rotation here. These are instabilities in sort of just stratified plasmas. See, MRI is the generalization of Rayleigh's criterion. I mean, if you have a rotating flow with some rotation profile, the hydrodynamic stability criterion is the Rayleigh criterion, okay, which is determined by the variation of L, specific angular momentum. There's like a close analogy here. So with the introduction of magnetic fields, the criterion goes from L to omega, rotation frequency in the case of MRI. Here, because of conductivity, the stability is determined not by entropy gradient but by temperature gradient. Because magnetic fields act like conduits to transfer angular momentum in the MRI case, and here thermal energy, I mean, they want to make this isothermal. So there is a close analogy, but this is not MRI.
The one that didn't switch off, if you had a different magnetic boundary condition, would it switch off? Is it?
Yeah, it would switch off.
If the field could just go all the way through, it would just somehow.
Right, so actually just the movie had a weird boundary condition. Everything else sort of was periodic in this direction. So
No, but you had an instability that the field started horizontal, kind of did something but went complicated, and
right.
didn't switch off. If you had different magnetic boundary conditions.
So, for example, if I had a boundary condition which does not allow,
What were you magnetic boundary?
So if you had a magnetic field boundary condition like this, which is reflective, it doesn't allow magnetic field lines to open up,
Yeah.
then it would switch off.
But in the one a bit further on, can you just...
This one. No, next.
No.
This one.
Yeah, what was your...
So basically the boundaries here are outflow boundary conditions, but we also have a stably stratified layer here, so that there's no, basically a neutrally stratified layer here, so that the boundary here doesn't make a huge influence on the flow.
What does the field do?
It just sort of penetrates, it just goes through it. So basically this is different from the movie that I showed where field was forced to not open up. So you can see that it's sort of starting at smaller scales and then just sort of becomes a larger scale. This instability grows at all scales as long as conductivity is important at that scale.
Any more? Okay, let's thank Prateek again.